So in this video, I'll be covering the premise of this lab and also what you'll be collecting in terms of data, and then how you'll be, I want to say analyzing, but more like calculating, what you'll be calculating, and then what you can conclude from that. So this lab is about thermodynamics, and in that lecture chapter, we learned about spontaneous processes and how these are the chemical and physical changes that occur without like an input of energy, meaning they quote unquote occur naturally. So they will happen on their own in a specific set of conditions. So it has to be like that set of conditions that fit the criteria to make it spontaneous. And we learned about something called Gibbs free energy, which is essentially the energy you kind of have left over from a process. And that value tells us whether something will be spontaneous at a certain temperature, given whatever enthalpy it is, given whatever entropy change occurred. So those are the three factors that affect Gibbs free energy, and Gibbs free energy tells us whether something is spontaneous or not. So entropy is denoted with a delta S, or entropy change, better yet. And enthalpy change is delta H. And then T is your temperature. So you can see how all three of these affect your overall Gibbs free energy. And here, this is a nice chart that kind of lays out what different types of changes will occur, and like the different scenarios that you can have, and how overall your delta G will be affected. And from that, whether you have spontaneity or not. So for example, when you have a delta H that is negative, what this means is that you have an exothermic reaction. A positive delta S means you have an increase in entropy, which is favored by the universe. Overall, this would cause a negative term right here for your temperature being multiplied by your entropy. And because of this, when you subtract this term away from your delta H, you end up getting a very negative delta G. Negative delta G means spontaneous. And for this particular scenario, case, whatever you want to call it, you will always have a spontaneous process because of that exothermic reaction and increase in entropy. Basically, the universe is like, yes, I like both of these, so whatever temperature it is, it doesn't matter. You'll always have spontaneous process. This right here is the opposite case. So this is an endothermic reaction. This is a decrease in entropy. So overall, you'll have a positive term on this side, and you end up getting a positive delta G. This is the opposite. And then you have the two cases where it depends on the temperature. So when you have an exothermic reaction, this is favored by the universe, but a decrease in entropy, this is not favored, then this one will be dependent on the temperature. So at low temperature, you'll have a negative delta G, so you'll have a spontaneous process at a low temperature, and then the opposite, of course, is true. And then here, again, opposite scenario, so these are both positive. So at high T, high temperature, you will have spontaneous process. So you've already studied these scenarios, hopefully in lecture, but this is just the same type of table showing you different scenarios, except it's formatted a little bit differently. I do like this table because it has this extra column which shows you how overall this term will be affected in terms of the sign. So knowing that information, those different scenarios, you're probably thinking, okay, So how are these things actually measured? Or maybe you're not thinking that, but it's okay. If we look at these different parameters, let's say we wanted to calculate delta G. We would need all of the parameters, meaning all of these. Delta H, temperature, and your entropy. If we had all of those, you could easily just plug them into your equation, get your delta G. Measuring the temp, obviously not difficult, right? We have thermometers, super easy. And we do have good methods to determine delta H. With that, you just need a closed, completely closed environment in order to measure like the heat given off or required for a system. So those are fine. But delta S is the one that's difficult and very impractical, impossible, along with Gibbs free energy as well. Like those are just kind of difficult to measure. So what we have to do is measure them or calculate them indirectly. So you can measure other things, use equations that allow us to get to whatever unknown, in this case Gibbs free energy, through a mathematical relationship, and in that way we can measure it. So for example, for us, we are going to first determine the equilibrium constant. So we are going to find these first in order to solve for this. So as you can imagine, you're probably going to have to do some algebra, you're going to have to divide both sides, you're going to have to do some sort of anti-log because you have that ln right there, so I'll leave that up to you, but that's the main idea here. We are solving for equilibrium constants in order to solve for delta G because we can't measure delta G directly. And this is true not only on this virtual lab, but also like in actual lab, it's difficult. So in this lab, this is the system, the equilibrium system we're working with. We have a cobalt hydrate reacting with chloride. You end up getting cobalt chloride and waters. And because we have this equilibrium system, we can shift it either way, which we learned about that concept previously. And anytime we adjust temperature, that will shift the equilibrium. If it adjusts the equilibrium, it's going to adjust our delta G. So because of that, we change the temperature, it ends up changing our equilibrium, our concentrations, and then that ends up changing our delta G. So in this simulation, you will be able to see all the concentrations of each of these substances. Now, pay attention to the states and which ones are actually part of the equilibrium calculation. So if you remember, your K equals your products divided by your reactants. So in this case, I'm giving you a hint there. Something like a liquid would not be taken into account. Remember, it's only aqueous and gases that are taken into account. Solids and liquids are never part of your equilibrium expression. So you're going to calculate your Kcs from the concentrations that you see in the mixture after adjusting temperature. These measured values of your Kc that you determine can be used to determine delta G. As I stated, remember, this relationship right here is the one that allows us to connect our K to our delta G. From there, you will, calculate all of that, and then you will plot your delta G versus T. So your delta G will be your Y, and your T will be your X. And the reason for this is because it will fit this equation right here. The line that you generate from this graph will fit that equation right there. And just to show you how it fits and what we're making the parallel too. So you all know about y equals mx plus b. I know you're sick of hearing that, but that's what applies here. So y, I'm going to write it up here first. Y equals mx plus b. We know that m is the slope, x is your, your variable, and then b is your y-intercept. So if we rearrange this, we can make it kind of match up to this delta G equals delta H minus T in entropy. So actually this should be mx plus your B is over there. So it's just a little bit rearranged, but hopefully you can see the parallel between the general algebra version of it and what we're working with, the line that we're working with. Okay, so in this video, I'm kind of just showing you generally what you're going to be doing. So first, obviously, you're going to click and open up your virtual lab. I just reloaded it so you could see it load. And then here, what I'm doing first is getting the glassware that I need for the first step. I'm getting a 100 ml volumetric flask. And then I'm getting the solutions that I'm going to use to make my dilution. So the solution you need is your HCl, and you need some water, because what you're doing is you're making a dilution. I'm going to leave it up to you to use M1 B1 equals M2 V2 to calculate how much of this solution you actually put into here, which I kind of went fast, but I showed that. And then you add water to dilute it. And then what you have there, once you finish making that, once you finish adding in the correct amount of HCl and also of your 12 molar HCl and your water, you should have a 6 molar HCl solution in that volumetric flask. So then I got everything else out of the way, so that's what you see me doing there. And now what I'm doing is I'm gathering my 250 ml empty Erlenmeyer flask in order to make my mixture in. So I also gathered my 1 molar cobalt chloride. And in here you can see me typing 50, 55, 45. You just pick whatever volume you want, record it obviously. You pick whatever volume you want between 40 and 60 and you add it to your flask. After that, you add in 100 ml of that 6 molar HCl that you made. So you would add that in, mix it, it mixes. So once you have that ready, you can look over here on this information tab and it will have all the concentrations of everything you need, of this, of the chloride, of the cobalt chloride. So that's where you record and that's where you see all your data. Now after that, you will insulate this by right-clicking, and then you will click Thermal Properties, Insulate from Surroundings. Once you insulate, you can change the temperature right there. So you can change it from like 20 to 25 to 30. So you saw me change it like from 25 to 30, I believe, and the temperature goes up over here and it's completely insulated. And once that temperature changes, you will also see some changes in molarity right there on that information tab. Now, I didn't show it obviously because I didn't actually have anything in there, but that's what you would see whenever you do it on your own. So then after, let's say you chose like, I don't know, 15 degrees C for your first temperature. You would repeat this same step with 3 additional temperatures, record all your concentrations of everything so you can calculate KCs for all those separate temperatures. Because you're going to be repeating this with 3 additional temperatures. So we went over this pretty much already, everything, but I'm going to go through it one more time. So you are going to record each temperature that you're choosing. So you can do that at the beginning if you want. You are going to, like even before you write down all the molarities of everything, you can, after actually doing each temperature and seeing what the concentrations of everything was for each temperature, you record them in the table that I have. Make sure to record all 3. After that, using these, you can calculate your Kc. Remember, Kc will be your products, the concentrations of your products over your reactants. So you set up your Kc equilibrium expression first, show me that in your sample calculation, and then, plug and chug. And you only need to show it once, so that's what I mean by sample calculation. Just show me like the overall expression from the equilibrium system equation, and then show me like one of them being calculated. And you will use the concentrations, obviously, that you recorded here. After calculating all your Kc's, you will calculate your delta G using this equation. Like I said, I'm leaving it up to you to do the algebra. You will have to do a little bit of algebra to solve for I just realized you don't have to do algebra. So I think I said that a little bit earlier. You don't have to do algebra. All you have to do is plug it in. Plug in your temperature, plug in your R value, and do the natural log of it, and you will get your delta G. I don't know why I was thinking that. Anyway, obviously you can see this semester has gotten the best of everyone. But yeah, you'll use your K's, plug them in with your appropriate temperature and your R values. Don't forget this negative sign right here. And then you end up getting your delta G's. So pretty easy. And just show your sample calculation. And then you will plot these delta G's on the y-axis and your temperatures on the x-axis. You will right-click, add a trend line. So this skill right here of plotting you learned in lab 2. So if you are rusty on that, go back to lab 2 and I go through it step by step. So if you need to go back, reference that, or you can ask me also. But you would add a trend line. This trend line would show you a linear equation, and from this linear equation you can determine delta H and delta S. And this goes back to what I said, how this parallels y equals mx plus b. And again, I'll remind you, y equals b plus mx. And like I said, I'll let you do the math on that, solving for each of them. Show your sample calculations of how you solve for each of these, and then just report both delta H and delta S in the little table that I have. And then finally, just some discussion questions. So, these might be kind of open-ended, but I just want you to analyze your data a little bit. And it just has to do with kind of connecting what you did and what you calculated to the actual, content and theory, what's the word I'm looking for? Concept of Gibbs free energy, spontaneity, all of that. So, don't feel like you need to write a whole academic journal or anything, just 3 to 4 sentences, kind of making a conclusion of whatever you think is the answer for this. If you have any questions, let me know. I'm sorry for uploading this so late, but better late than never, right? Anyways, email me if you have any questions.